Okay, so with 54D2, we're really looking at today what happens when we have a nonlinear transformation. So if we yesterday we looked at the M&M example. They worked with the partner to figure out if you have nonlinear data, what do you do, right? And honestly, we don't manipulate the line, we manipulate the data. So sometimes the scatter plot does not show a linear pattern. Often the data exhibits some sort of curved pattern. To fit the curve to a data set, we transform X or Y so that the scatter plot of the transformed data has a linear appearance so that we can use methods of the least squares regression line to find the appropriate model. So it's kind of weird. Instead of manipulating data, or instead of manipulating the line, we manipulate the data. So here's kind of our general model. So we usually start off with X and Y, and we're given Y hat equals A plus BX. So this has no transformations at all. If we think it's linear, we go with that. Now, if it looks curved, like the M&M example yesterday, we might log Y. So we'll have X comma log Y. So then our line becomes log Y hat equals A plus BX. We call this the exponential model. So that's what you did yesterday with the M&Ms. We did an exponential model. Now, if that still doesn't work, we'll log both X and we'll log Y. So then our equation is log Y hat equals A plus B log X. Okay, this is called the power model. Now, sometimes if we don't want to use Y, we can use the natural log of ln. So sometimes you'll see ln instead of log, but they're interchangeable. So what we're going to do, our big example of the day, is farmers all over the world face the problem of soil erosion. A recent paper reported on a study of the relationship between wind velocity X and soil erosion Y in a very dry environment where erosion control is especially important. So we're going to go through and do everything with the data. I did not put this data in my calculator, so I'm going to pause the video and put the data in my calculator, and then I'll come back. Okay, so I put all the data in my calculator. So one way to transform the data is by taking logs of the Y variable. This will find an exponential curve to fit the data. So think about back to algebra. Your exponential equation is Y equals A times B to the X power. Usually this is your constant, and this is your growth or decay factor. Okay, we write ours as log Y hat equals A plus BX. I will show you eventually how these two relate. I think the last problem on here is how to change it so you can see sort of how that works. But they are equivalent equations. So transform the data by taking the log of Y and placing it in list 3. Sketch the scatter plot for log Y versus X. So I'm going to take my list 2. I'm going to go to list 3 and highlight it. I'm going to do log list 2. So I'm going to log my Y variable. Now I'm going to do a scatter plot, list 1, list 3. So zoom 9. So what we have here, we're just going to do a slight sketch. We have wind velocity on the bottom. Okay, then we have the log of soil erosion. So if I look now, it sort of looks linear. Just sketch it like that. So it looks like it's a strong, positive, linear relationship. Without actually doing any calculations, this is just based on the scatter plot. Okay, so find the least squares regression line of the transformed data, report it in a proper way. So now I'm going to do stat calc 8. But I don't want list 1, list 2, I want list 1, list 3. Now if you have an older calculator, this doesn't pop up, you're going to have to do list 1, comma, list 3. Otherwise it'll default to list 1, list 2. So there's my equation. So I have log y hat equals negative 0.243 plus 0.103x. Again, let's define our variables here. X is the wind velocity. Log of y hat would be the log of the predicted soil erosion. Okay. Find and interpret the correlation coefficient. So here R is 0.933. So just like I said before, there is a strong positive linear relationship between wind velocity and the log of the soil erosion. So the good thing about this chapter is a lot of the stuff repeats. All we're doing in this section is stuff we've already done. We're just adding the log of. So sketch a new residual plot. So we found our least squares regression line. Now you won't have to do this. So stat, when I go to list 4, second stat, hit residual. I don't think that's going to work. Then I want to do list 1, list 4. Okay, there it is. You seem like large numbers. So you got a couple up here, a couple at the bottom, but it looks pretty random. So we would say no pattern in the residual plot. Therefore, the transformed model, transformed linear model, is appropriate. Okay, so we transformed it. Now we're saying it's okay. Predict what the soil erosion would be if the wind velocity was 40 kilometers per hour. So we're going to have log of y hat equals negative 0.243 plus 0.103 times 40. Now, the problem is, once you actually do this, negative 0.243 plus 0.103 times 40, you get log of y hat equals 3.877. You can't just stop there. We actually want y hat. So you got to think all the way back to algebra. To get rid of a log, I'm going to exponentiate. So I'm going to take these to the 10th power, and those will go away. So really y hat is 10 to the 3.877 power. Oops. So y hat is 7,533.56 kilograms a day. So all I did in the calculator was, once I got my answer, did 10 to the answer power. Comment on how accurate you expect your prediction to be to x equals 40. Let's go back. If we look, our wind velocity is really only from 13 kilometers per hour to 27, so we really shouldn't have done that. So since the value is outside the range of the data, we don't expect this predicted value to be accurate. Remember extrapolation. We can't extrapolate. Oops, I spelled it wrong. We can't extrapolate past the range of the data. And we talk about that with the second part of the M&M worksheet with the AIDS model, about how if you were to predict the amount of AIDS cases in like 2006, it's like some million people, and really it hasn't been that, because that's outside our range of our data. So find and interpret the coefficient of determination for the transformed data. Instead of going back and doing the whole thing again, I'll just tell you R squared is 0.87. So now we just got to memorize our interpretation. So 87% of the variation in the log of soil erosion can be explained by the linear relationship between wind velocity and log of soil erosion. So all of this could be an FRQ on your test. Nothing in here is new. Again, we're just adding the word log to everything. Interpret the slope. So for every additional kilometer per hour increase in wind velocity, we predict a 0.013 kilogram a day increase in the log of soil erosion. Okay. So now I definitely wouldn't ask you. I'm going to transform the equation so it's in terms of y and not log y. Again, this is just so you could see how this is actually an exponential model. So we have log of y hat equals negative 0.243 plus 0.103x. So again, I'm going to exponentiate just like I did for part E. So I'm going to take to the 10th power to the 10th power. So I get y hat is 10 to the negative 0.243 plus 0.103x power. Now, this is what you did yesterday. I can continue to do my log rules and simplify this. When I have a plus, that's really multiplying. So now it's y hat equals 10 to the negative 0.243 power times 10 to the 0.103x power. Now, these are just numbers. So if I do 10 to the negative 0.243 power, I get a number, 0.571. So y hat equals 0.571 times, there's another number, so 1.268 to the x power. So there's my exponential equation. Here's my constant, and there's my growth factor. So again, this is just using algebra rules to transform what we do to what you've seen before. So stick with what we do because I feel like it's a lot easier, especially since we are interpreting things, and you can find r and r squared a lot better. But all we're doing, like I said, is transforming the data so that it fits the linear models so that we can do all of our linear stuff. And that's really it.